Determinants.
Hi, Radha.
Hi, can you tell me something about matrices?
Yes, sure.
Look at this structure of matrix. I have to find its determinant.
Okay, A is equal to E, F, H, I.
This structure is not a matrix, it is a determinant structure. Isn't a matrix and determinant same? No, they are different. The determinant is a number which tells us the uniqueness of solution for a specific matrix. Oh, I'm confused. Come, let's learn more about determinants. After completing this learning module, we will be able to understand determinants, study properties of determinants, calculate minors, cofactors of determinants, understand applications of determinants like finding area of a triangle, adjoint and inverse of a square matrix. Check consistency of a system of linear equations. Find the solution of linear equations using inverse of a matrix. Determinants. Determinant. For a given matrix A, the number A1, 1 into A2, 2 minus A1, 2 into A2, 1, which determines the uniqueness of solution, is called the determinant of A. The determinant of a matrix A is denoted as determinants in different dimensions. Determinant of a matrix of order 1. Let X equal to X be a matrix of order 1, then the determinant of X will be determinant of a matrix of order 2. Let X equal to U, V, W and X be a matrix of order 2, then the determinant of X will be U, X minus V, W. Determinant of a matrix of order 3. Let X equal to A, B, C, D, E, F, G, H, I be a matrix of order 3, then the determinant of X will be we get determinant of X equal to A into E into I plus C into H into D plus B into F into G minus C into E into G minus F into H into A minus I into D into B. This is the value of determinant for a matrix of order 3. For example, calculate the determinant of the given matrix X equal to 1, 5, 0, 2, 2, 1, 0, 4, 3. Solution. Given X matrix is calculating determinant of X finally gives us determinant of X as minus 28. Properties of determinants. Some of the properties of determinants are as follows. Property 1. On interchanging the rows and columns of a determinant, its value remains the same. For example, X is equal to, so its determinant will be given as, let it be equation 1. Changing the rows and columns of X, we get X equal to. Now the determinant will be given as, let it be equation 2. Equations 1 and 2 are equal, which implies property 1. Property 2. On interchanging any two rows or two columns, the sign of the determinant changes. For example, X is equal to, so its determinant will be given as X equal to, let it be equation 2. Interchanging first and second rows, we get X equal to. Now the determinant will be equation 1 and 2 proves property 2. Property 3. If any two rows or two columns of a determinant are exactly the same, then the value of determinant will be 0. For example, x is equal to, so its determinant will be 0. This proves property 3. Property 4. If every element of a row or a column of a determinant is multiplied by a constant number, say m, then its value gets multiplied by m. For example, x is equal to, multiplying second row by m gives determinant of x. This proves property 4. Property 5. If the elements of a row or a column of a determinant are expressed as sum of two or more terms, then the determinant can be expressed as the sum of two or more determinants. For example, x is equal to, we can write it as, this proves property 5. Property 6. The value of a determinant remains unchanged if we apply the operation Ri changes to Ri plus k into Rj to any row or any column of a determinant. For example, x is equal to, it gives the determinant of x as 0. This proves property 6. Minors and cofactors. Minors of a determinant. A minor of an element, say A12 of a determinant, is the determinant obtained by omitting its first row and second column in which A12 element lies. The minor of an element A12 is denoted by capital M12. For example, calculate the minor of the element 5 in the determinant. Solution. As we can see that 5 lies in the second row and second column, its minor will be M22. Its minor will be given by the determinant obtained after omitting second row and second column of the given determinant. The left determinant is the minor of 5 is M22 is equal to 1379. This on further simplification gives M22 as minus 12. So the minor of element 5 is minus 12. Cofactors of a determinant. The cofactor of an element Aij is denoted by capital Aij. In general, the cofactor of an element Aij is defined as capital Aij is equal to minus 1 raised to power I plus j into capital Mij, where Mij is the minor of Aij. For example, find the cofactors of all the elements of the given determinant with elements 1, 3, 7, 9. Solution. First of all, we will calculate minors of all the elements of this determinant. Minor of the element A11 is 9. Minor of the element A12 is 7. Minor of the element A21 is 3. Minor of the element A22 is 1. Now the cofactors can be calculated as follows. Cofactors of the element A11 is capital A11 is equal to minus 1 raised to power 1 plus 1m11, which gives us 9. Cofactors of the element A12 is capital A12 is equal to minus 1 raised to the power 1 plus 2 into m12, which gives us minus 7. Cofactor of the element A21 is capital A21 is minus 1 raised to the power of 2 plus 1 into m21, which gives us minus 3. Cofactor of the element A22 is capital A22 is equal to minus 1 raised to the power 2 plus 2 into m22, which gives us 1. Applications of determinants. Some of the applications of determinants are discussed below. First, area of a triangle. as we are known to the fact that the area of a triangle with vertices A1, B1, A2, B2 and A3, B3 is given as area is equal to 1/2 of A1, B2 minus B3 plus A2, B3 minus B1 plus A3, B1 minus B2. We can write this expression in the determinant form as for example, find the area of a triangle whose vertices are given as 1, 4, 3, 8 and 5, 1. Solution. We know the expression for area is, this implies determinant of area is given as, this implies area is 1/2 into minus 22, which gives area as minus 11. Second, adjoint of a matrix. The adjoint of a square matrix Aij with order n by n is defined as the transpose of the matrix formed by cofactors, that is capital Aij with order n by n. The adjoint of the matrix A is denoted as Adja. For example, find adjoint of A for the given matrix A. Solution. First of all, we will find minors. M11 is 2, M12 is 1, M21 is 6, M22 is 3. Now the cofactors will be A11 is 2, A12 is minus 1, A21 is minus 6, A22 is 3. The matrix formed by cofactors is A is equal to plus 3 minus 6 minus 1 plus 2. Taking transpose of A, that is interchanging rows and columns, we get adjoint A as plus 2 minus 1 minus 6 and plus 3. 3. Inverse of a matrix. The inverse of a matrix is given as A inverse is equal to 1 by A determinant into adjoint of A. Note, singular matrix. The matrix for which determinant is 0 for which A inverse doesn't exist. Non-singular matrix. The matrix for which determinant is not equal to 0. For example, in the previous example, find A inverse. Solution. Since matrix A is given and we have calculated adjoint A as, let's calculate determinant of A, which is found out to be 0. It means that the given matrix is a singular matrix. For the given matrix, A inverse doesn't exist. Consistency of linear equations. Consistent system. If the solution of a system of equations exists, then the system is said to be consistent. Inconsistent system. If the solution of a system of equations doesn't exist, then the system is said to be inconsistent. Consider the system of equations P1x plus Q1y plus R1z equal to S1. P2x plus Q2y plus R2z equal to S2. P3x plus Q3y plus R3z equal to S3. Let P, X and S be the matrices given as. This system of equations can be written as Px equal to S, that is, special cases. First, when P is a non-singular matrix, then its inverse exists. Now Px equal to S. Pre-multiply both the sides with P inverse. P inverse P, X equal to P inverse S. This implies X equal to P inverse X. Second, when P is a singular matrix, then P determinant is 0. Here we will calculate adjoint PS. Case first. If adjoint P, S not equal to O, O is the zero matrix. In this case, solution doesn't exist and the system of equations is inconsistent. Case second, if adjoint P, S is equal to O, O is zero matrix. In this case, system may have either many solutions or no solution. So, the system of equations may be consistent or inconsistent. For example, solve the given system of equations and check whether the system is consistent or inconsistent. Solution. The given system of equations can be written in the form Px equal to S, where P equal to X equal to S. The determinant is found out to be P determinant is found out to be minus 17. That is P determinant not equal to 0, which means that P is a non-singular matrix. We will use X equal to P inverse S. First, let's calculate P inverse. We know the relation. Here P determinant is minus 17 and cofactors of P are as follows. So adjoint P is given as, thus P inverse is given as. Now X equal to P inverse S. This implies X, Y, Z is equal to minus 1 by 17, minus 17, minus 34, minus 51. This further implies X, Y, Z is equal to 1, 2, 3, which implies X equal to 1, Y equal to 2, and Z equal to 3. Let us summarize what we have learned in this chapter. The determinant is a number which tells us the uniqueness of solution for a specific matrix. On interchanging the rows and columns of a determinant, its value remains the same. On interchanging any two rows or two columns, the sign of the determinant changes. If any two rows or two columns of a determinant are exactly same, then the value of determinant will be 0. If every element of a row or a column of a determinant is multiplied by a constant number, say m, then its value gets multiplied by m. If the element of a row or a column of a determinant are expressed as sum of two or more terms, then the determinant can be expressed as the sum of two or more determinants. The value of a determinant remains unchanged if we apply the operation Ri changes to Ri plus k into Rj to any row or any column of a determinant. The minor of an element A12 is denoted by capital M12. The cofactor of an element Aij is denoted by capital Aij. Applications of determinants are area of a triangle, adjoint of a matrix, and inverse of a matrix. If the solution of a system of equations exists, then the system is said to be consistent. If the solution of a system of equations doesn't exist, then the system is said to be inconsistent.